I don't think it's going to be easy for you to see this effect, but if I have a laser beam of a certain intensity and bring a polarizer in front of it, the intensity gets reduced by half. Now you should notice this effect almost instantly, because otherwise the iPhone auto adjusts its contrasts. So you can see that the intensity clearly drops. That intensity reduction by a factor of half is a very important principle in polarizers. Polarizers are commonly found in sunglasses, even these cheap sunglasses that I only paid $10 for from some drugstore. So these polarizers do the trick of keeping sunlight and snow blindness of your eyes. So what is the phenomenon of polarization? White light, as it normally occurs, has got all directions of oscillation. So if I look at a beam of light coming toward me, the electric field oscillates in all possible directions. It's going to oscillate. I'll just draw a few of these: north, south, east, west, and northwest, and south, southeast, that type of thing. It's going to oscillate in all directions with no preferred direction of oscillation. Now, if you pass the light through a polarizer is a device which filters out just one direction of oscillation. So a polarizer is typically made up of long polymer chains of material. So you take this, when you build a polarizer, you cause polymer chains to be deposited along a certain direction. So I'll indicate these polymer chains by putting random atoms here and there. So once you have this polarizer constructed, what it'll do is it'll select out that direction preferentially as opposed to any other direction. So once light goes through this polarizer, it's going to come out marching looking like this. The main intensity that of light is going to be comprised of just this type of oscillation. All these other oscillations, for example, east-west, southeast, all that is cancelled out, and all you have is a north-south oscillation after it goes through a polarizer like this. Now, how does that account for a factor of half or 50%? Well, that comes from the expression for the electric field itself. The expression for the electric field oscillating in space and time, E of x comma t, is E naught sine or cosine kx minus omega t. Now, the intensity is proportional to the square of the electric field. So you're going to get something like E naught squared cosine squared kx minus omega t, which I'll not write. Now, when you have light like this, the intensity is got by taking the average. So the average of the intensity will have this factor of half come in, because the average of cosine squared is half. So we'll call that I naught. Whatever you get from this, we'll call that I naught. Now let's see why this other factor of half comes in when you have light go through a polarizer. So the average intensity is I naught, and then light is going through a polarizer. Why is that intensity coming out I naught over 2? Let's figure that out. The reason for that is the following. If you have a beam of light making some angle, let's say an angle theta here, then only the component that is in the direction of the polymer molecules will make it through, because the north-south component is that direction. And the component that makes it through, which we'll call E parallel, is going to be E naught cosine theta. And this theta is completely different from that kx minus omega t business. So that's what makes it through. And the intensity that makes it through, which we'll call I parallel, is going to be proportional to E parallel squared. And that's going to be E naught squared cosine squared theta. Now, light is going to come for all angles of theta, so we have to average this again. So the average of I parallel is going to be the average of E naught squared. There's also this other thing of cosine kx minus omega t. I should write that here. Cosine kx minus omega t squared. So when you do that average, the average of this is already I naught. And so I'm going to get I naught times the average of cosine squared theta. Now the average of cosine squared theta is half. Here's a cheap and easy way to see it. You know that sine squared theta plus cosine squared theta equals 1. The one way to conceptualize that factoid is the following. If you draw the graph of sine squared theta, it looks like this. Just try it. It's never negative, and it goes like that, where these things are pi, 2 pi, and so on. The graph of cosine squared theta looks exactly the opposite. So at 0 it's 1, so the cosine squared theta graph looks like this. Now when you add these two graphs up, you're going to get 1. The average value is going to be 1. The value is going to be 1 if you add these up. That means the average value of cosine squared theta is equal to the average value of sine squared theta, because the graphs look identical except that it is placed by pi by 2. And so each one is going to be half. That's an easy geometrical proof of this fact. And so we have our famous result, the result that the polarizer admits a light, I parallel, which is equal to the original intensity divided by 2. The second rule, that's the first rule of polarizers. The second rule is, if you pass this light through another polarizer, what happens? Well then, this is already marching in the north-south direction, and if you pass it through another polarizer which is making an angle of say phi with respect to this one, then you're going to get this situation. I'll draw this other polarizer. Polarizers are usually indicated by drawing the polymer bonds but not putting any atoms, because it's difficult to draw that. So you take this light that's coming in like this, and it's making some angle of a different angle. I've already used up theta there, so I'll use this angle phi. So already polarized light, whose intensity has already been reduced by half by passing it through some initial polarization. I'll talk about how this initial polarization occurs in some situations in nature, but right now assume that you've marched a random white light through a polarizer first to get it marching in step, and then you come to a different polarizer which makes a different angle. Well, the same principle holds, except this time you don't worry about too many of these things. You just directly do the calculation, and you find that only the cosine phi component makes it through. And so you're not going to average though over all these angles theta, because this is one specific north-south angle. So you don't average it. That's the only difference. So what comes out, I out, is going to be I in times cosine squared phi. The person who discovered this first is Malus. And so this is called Malus's law of polarization. An already polarized light, when passed through a polarizer that makes an angle of phi, has got an intensity equal to that. So to summarize both these laws on the optical axis, what I'll do is I'll draw a cartoon sketch of both of these things. So you have random white light polarized in all directions come into a initial polarizer, and then that polarizer will send out light like this. So that's intensity I naught. That's intensity I naught over 2. And then you have a second polarizer that's placed at some angle. Well, this time I'll call that angle theta again. And then this new intensity that comes out, first of all, it'll be tilted to the new plane of polarization. It's going to be I naught over 2 cosine squared theta. So that's in a nutshell everything that I have discussed so far. You can have any number of polarizers, and in the limit, as you have n equals infinity polarizers, you have the phenomenon known as Faraday rotation. So this is all very fascinating, and our man Faraday, who was responsible for many things in electricity and magnetism, also tried his hand at optics. And Faraday rotation is displayed by things like corn syrup. You have a corn syrup cylinder full of corn syrup, and I still remember doing this experiment as an undergrad. You take the cylinder full of corn syrup and then you see how these rotations happen. That's called Faraday rotation. So that's the subject of polarizers. There's very little talk about it except how this occurs in nature. In nature, if you have something like sunlight, and this might be of interest to some of you who do boating and other activities in the summer, sunlight's coming towards the water. Well, sunlight's going to be made up of sunlight's junky. It's going to have all kinds of directions of polarization. Well, what's going to happen here is when there's a first reflection of sunlight, by the law of reflection, this angle is equal to this angle, then this light is going to come out almost entirely polarized, and the polarization direction is going to be parallel to the plane of the interface. So I'll draw this as bullets, and then here, when you refract it, since it's water, it's going to bend towards the normal by Snell's law. The refracted ray is going to be partially polarized, which means it's going to have some bullets, and it's also going to have some things like that. So that's partially polarized light, and that's fully polarized light. This effect is maximum when this angle is 90 degrees. And when this angle is 90 degrees, the light that comes out is almost entirely polarized. So please don't confuse this 90 degrees with anything else. There's a critical angle phenomenon we learned from refraction. That's the light going from here and coming at 90 degrees to the interface. This is completely different. So this criterion of getting a polarized light was discovered by Brewster. And so it's called Brewster's criterion. Brewster's criterion is this. If the refracted ray and the reflected ray make an angle of 90 degrees, then the reflected ray is almost entirely polarized light, and the refracted ray is partially polarized light. The proof of Brewster's criterion is beyond the scope of this course. You need graduate course for that. But we can certainly do something from our study of Snell's law. So if this is theta and this is theta prime, then we know that theta prime plus 90 equals 180, which means theta plus theta prime is going to be 90 degrees. Also, we know that n1 sine theta equals n2 sine theta prime. That's Mr. Snell's contribution to science. So we can substitute, since theta prime is equal to 90 degrees minus theta, I can substitute that here, and I get n1 sine theta equals n2 sine of 90 degrees minus theta, which, if you remember your trigonometry, is cosine theta. Well, there you go. The criterion for Brewster's angle is obtained like this. So tan theta b, in honor of Brewster, we call this angle theta Brewster, is going to be sine over cosine. So I'll get that by bringing the cosine down here and taking the n1 down there. It's n2 over n1. So go out on a nice sunny day, and n2 for water is 4/3, n1 is just 1, and look for theta b, which is tan inverse of 4/3. If the sun is at that angle and you have and you're looking at the reflection of the sunlight and you're wearing sunglasses, try the following experiment. You're looking at the sun's reflection from the lake when the sun is at that angle, at the theta Brewster angle, which is given by this condition. It's usually around 2 o'clock in the afternoon at this latitude. You look at the sunlight, and then you turn this by 90 degrees. When you turn this by 90 degrees, you'll see complete darkness, because there'll be no reflection at all, which means that you won't see any reflection of the surface. You can see down to the bottom of the lake if you do this experiment. So that's the beauty of Brewster's criterion for polarization. Other areas where you get polarized light of reflection include metallic surfaces, and this is used to good advantage in nature. Insects and other beetles have shiny surfaces of which polarized light gets emitted, and then they confuse the prey like that.